Now we're going to put everything together and show how when you use uh, more than one reference frame and the magic formula, you can make your life a whole lot easier in terms of solving the kinematics for a system. So we're going to go back to our example where we have a spider moving on a Roomba. So the center of our robot we'll define as point R, and the location of the spider is point S. And again, that spider can move in the radial direction along a single line, just inwards and outwards from the center of the robot. And we want to find the acceleration, which involves also finding the position and velocity of point S, where the spider is, with respect to a fixed frame A. So again, we have our fixed frame here. This is frame A, and it has two unit vectors, A1 and A2, and has an origin at point L. So again, to get the position vector, we want this, right? So R, O, S. And to get that, we take the sum of the following two vectors. This vector here, so R, O, R, which tells us where the center of the robot is in frame A. And this vector here, so this is R, RS. And again, this is where we're going to introduce our second reference frame. So we're going to put the origin of that reference frame at point R, and we're going to align the B1 axis along the line that the spider is going to travel. And we have then B2. And so now, and then of course, reference frame B is rotated by an angle theta with respect to frame A. Okay, so now let's go ahead and define, again, we want ROS, and that's the sum of ROR plus RS. And so ROR is just some magnitude in the A1 direction, so we'll call that U, and some magnitude in the A2 direction, so we'll call that V, plus, and then because we're using this second reference frame, we're now going to define this vector RRS in frame B because it's easiest, right? Here's our spider, and it's just moving along in the B1 direction, so we can simply write here R, we'll call R, that's the distance between, from the origin of the center of the robot and where the spider is, so we'll call that R. So we have R, then B1. All right, so now this here is our position vector. Okay, so the next step is, of course, to get the velocity of point S in frame A. So we take the time derivative of our position vector ROS in frame A. So that's going to look like this, ddt in frame A of U A1 plus V A2 plus R B1. So of course, taking the time derivative of UA1 and VA2 is quite easy, right? Because we're taking the time derivative in the in frame A, and these terms are written in frame A, so we can simply write U dot A1 plus v dot a2, and then we're going to keep this term here. Right, so now we have to take the derivative of this term, which used to be tricky, right? We had to substitute the relationship between B1 and the A1 and A2 unit vectors, but now we can simply use our magic formula, which again is d dt of a vector that's written in the unit vectors of B. If you're taking the time derivative in frame A, it's going to equal the following. You take the time derivative of that vector in frame B plus the cross product of the angular velocity of frame B in frame A with your vector V. So this portion here, I'm going to skip ahead slightly just because we went through this all in one of the prior videos. But ultimately this term here gives you could solve this out and get the following. You have u dot a1 plus v dot a2 plus, so you take the time derivative of v in frame B, so that gives you r dot b1. Then you have to take the angular velocity, which you can, in this case, write as, I'm just going to write this up here. This is theta dot b3. So you take the cross product of theta dot b3 with r b1, and just to write this out, write it out up here. So your final answer for the velocity of point S in frame A is u dot a1 plus v dot a2 plus r dot b1 plus r theta dot b2. Right, the cross product of b3 and b1 is b2. So there you have it. We used our magic formula, and now we have velocity. So next we have to get acceleration. Okay, so final step to get the acceleration of point S in frame A. So we need to again take the time derivative of our velocity vector in frame A. So that's ddt in frame A of u dot a1 plus v dot a2 plus r dot b1 plus r theta dot b2. And so you might recognize right away that, okay, now again we have to take the time derivative in frame A, but we have some terms that are written in terms of B1 and B2, so the unit vectors of frame B. So it turns out that we actually have to use the magic formula again. So first let's handle the easy terms, right? So we can just rewrite this again. Taking the time derivative of these two terms that are already written in terms of the unit vectors of frame A is easy, right? So we just have u double dot a1 plus v double dot a2. So now we have to take the time derivative of r dot b1 in frame A plus the time derivative of r theta dot b2 in frame A. So it turns out that we're actually going to have to use the magic formula twice here. So for the first time, so we have our u, just rewriting this out again, u double dot a1, v double dot a2. All right, so this first term, I'll just write all of it out. So we have ddt in frame B of r dot b1 plus, I will simplify this here, right? We know that the angular velocity is theta dot b3. So I'm just going to simplify a little bit. So we're just going to call that theta dot b3. And we take the cross product with r dot b1 plus we have ddt in frame B of r theta dot b2 plus theta dot b3. We take the cross product with r theta dot b2. All right, and then we just continue along. So we have our acceleration, our easy acceleration terms, a2. And the time derivative of this term here in frame B is r double dot b1. And you can factor out that theta dot and that r dot, and the cross product between b3 and b1 is b2, so we can write this as r dot theta dot b2. Next, we have to take the time derivative of r theta dot b2 in frame B, and so that equals r dot theta dot b2 plus r theta double dot b2, right, product rule. And then again we can factor this out here. So we have r theta dot squared, and then we have the cross product between b3 and b2, and actually that's a negative b1. And finally, we can just combine similar terms for the sake of completeness. So we have u double dot a1, v double dot a2, plus r double dot b1 plus 2r dot theta dot b2 plus r theta double dot b2 minus r theta dot squared b1. So now we've arrived at our acceleration of point S in frame A. And so our answer still has B1 and B2 terms. Of course, we could go in and plug this in and get everything written in terms of A1 and A2. That's not needed here. Now we have an expression, at least, that we can describe the acceleration of point S in frame A. And we did so using multiple reference points. And again, you can go back and you can check this, the correctness of this with your prior solution. So you can go in and plug in the equations that describe B1 in terms of A1 and A2 if you would like. And so that's it. We'll go through a few more examples in the videos and also in class, but this is the general procedure for using multiple reference frames and for using the magic formula to find the derivative when you have a vector that's written in terms of the unit vectors of the moving frame.